Hello there, and welcome back. In this video, we're going to close off our discussion of basic probability theory with just some last-minute comments on probability approximations, which are usually useful if you don't have access to software, tables, or other intuition and information about the distribution that you're actually sampling from or working with. So the very first distribution rule or approximation rule that you may have already heard of is known as the empirical rule, which can only be applied to normal random variables. So let's assume that x is a normal random variable, or something that is approximately normal, and let's assume that we know the mean and the variance of that random variable, and hence the standard deviation of it. So if we know that x is a normal random variable, and we have access to, say, software, or we know how to do integral approximations in calculus, then we know that the distribution of that random variable x is going to be equal to 1 divided by sigma times the square root of 2 pi e to the minus 1/2 times x minus mu divided by sigma the quantity squared. So technically, one can find the integral between any value you want, not just between standard deviations. But in particular, we know that we can integrate from mu minus sigma to mu plus sigma of this density function, and we can get some approximation to whatever decimal accuracy that we want. But, of course, this function is not the easiest to work with, so sometimes we want to use the standard normal distribution to do calculations, and that's, of course, perfectly fine. So we know that the standard normal distribution is going to be equal to 1 divided by the square root of 2 pi times e to the minus 1/2 x squared. A very, very useful or simplified version of the normal distribution. And we can find that this integral is going to be equivalent to the integral from minus 1 to 1 of the standard normal distribution. You will get the same exact answer. But again, let us assume you don't have access to integrals or calculators or tables or what have you. You maybe need an approximation to the probability that you're within one standard deviation of the mean, assuming that you are a normally distributed random variable. And one can find that this approximation actually comes out to 68%. So if we look at our normal distribution, and here is our mean mu, and we have mu minus sigma and mu plus sigma here, then the probability that you're within one standard deviation from the mean for a normally distributed random variable is approximately 68%. So of course we can extend this to 2 standard deviations, 3 standard deviations, and so on. So if we go beyond the mean, in particular by 2 standard deviations, that's of course equivalent to integrating from minus 2 to 2 of our standard normal distribution. And one can find that's approximately equal to 95%. So that means 95% of the population is always going to be between -2 and 2 standard deviations from the mean. And what about 99%? So keep in mind, the more and more you work away from the mean, the more percentage you're going to be covering. So as you increase the number of standard deviations you're moving away from the mean, the more and more this probability is going to become. So therefore, the integral from mu minus 3 sigma to mu plus 3 sigma of our normal distribution, which is equivalent to integrating the standard normal distribution from minus 3 to 3, and that's going to come out to approximately equal to 99.7% of the data. So if you go, 4 standard deviations of the mean, you would, think that it's 0.999 and so on percentages away from the mean. So this is what we call the empirical rule. So technically it's just a little shorthand rule to memorize, what percentage of the area lies between some standard deviations from the mean. And sometimes you're going to see some pictures right here. So let's assume this is minus 1 to 1, minus 2 to 2, and minus 3 to 3. So the empirical rule says this. So within one standard deviation of the mean, this is going to be 68% of the data. And if you're within 2 standard deviations of the mean, then that's going to be equal to 95% of the data. And if you're within 3 standard deviations of the mean, then you're going to have 99.7% of the data. So it's just some approximations to within, integer standard deviations from the mean, in particular 1 through 3. But if you want the probability that you're within 1.5 standard deviations, or if you want non-symmetric intervals on a normal bell curve, then the empirical rule is not going to be very helpful to you. right? So let's just look at a couple examples on how you may want to use the empirical rule and some of the problems that it can at least approximate, right? So let's assume that we want the probability that x is more than, so not within one standard deviation, but more than one standard deviation from the mean, right? Let's assume we want this particular property. So if we look at our normal distribution, let's assume that this is our standard normal distribution, so 0, -1, and 1. So that means we want the probability that we're within the tails of the distribution, in particular the one standard deviation tails of the distribution. So how do we find that? So this problem in probability form is just going to be the probability that the difference between x and the mean is more than one standard deviation. So from the complementary perspective, that's the same as 1 minus the probability that the distance between x minus mu is less than one standard deviation. And we can actually write this in an equivalent way. That's the difference, that's the same as mu minus sigma less than or equal to x less than or equal to mu plus sigma. So according to the empirical rule, that's approximately equal to 1 minus 68%, which is going to come out to 32%. Therefore, 32% of the data is going to be lying in these two tails, where these boundaries of the tails are one standard deviation away from the mean. So we could also solve, more than two standard deviations away from the mean. So how would we go about that? So the probability that you're more than two standard deviations away from the mean. Keep in mind that's the same as 1 minus the probability that the distance between x and the mean is less than two standard deviations of the mean. And again, that's equivalent to writing mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma. So from the empirical rule, we know an approximation to that. So the empirical rule is going to give us this approximation. So that's 95% of the data. So that means 5% of the data is going to lie outside of the two-tailed region, or the two standard deviation tails region. So that means this area right here, 5%. So those are just some of the basic properties that the empirical rule can solve. It's not very accurate, especially if you want some weird asymmetrical regions. Technically, you can find areas between regions. So let's assume that you want to solve this problem. So -1, -2, -3, 1, 2, and 3. So what's the probability that you're like in between these two regions, and let's assume you're in between these two regions. Technically, the empirical rule can give you an approximation to this, but if you have access to software, that's just going to be the integral from -3 to -1, plus the integral from 1 to 2 of the standard normal distribution. So you shouldn't be, too into these complicated problems, but some teachers enjoy doing those things, so to each their own. But technically integrals can solve these very quickly, and the empirical rule can too, as long as your integer standard deviations away from the mean. You just have to fill in the patterns and the pieces of the puzzle in order to solve those problems. But enough of that. Let's go to the next distribution that we're going to be interested in approximating. So the empirical rule allows us to approximate probabilities when we're working between standard deviations of the mean. But generally speaking, most populations are not normal. So the leading question then becomes, what if x is not a normal random variable, right? So the distribution can look practically like anything, right? So let's assume that the area under this curve is equal to 1. So what's the probability that you're within one standard deviation of the mean? And of course, that need not be symmetric if it's not a symmetric distribution, right? So is there ways to approximate this area? The answer is yes. So one of the ways that you can sort of approximate this is what is known as Chebyshev's theorem. So Chebyshev's theorem. And Chebyshev's theorem says this. So the probability that the distance between x and mu is less than k standard deviations of the mean, so 1, 2, 3, and possibly even decimal standard deviations from the mean, is always greater than or equal to 1 minus 1 over k squared. So it doesn't tell you that the probability of this event occurring is approximately equal to something. It gives you a lower bound on that probability. So it's like, the probability of this event is more than 10%, or it's more than 5%, or it's more than 80%, or something like that. So technically, this may be viewed as weaker than the empirical distribution, but keep in mind, this is actually for all random variables, right? And that's a very, very strong statement. So yes, it doesn't give you approximations in the common use of the word approximations, but it gives you lower bounds and possibly upper bounds for probabilities. Because we know that all probabilities are between 0 and 1, so technically we do have an upper bound for this particular probability statement of 1, and we have a lower bound. But keep in mind, this is only useful for k bigger than 1, because when k is equal to 1, then that's going to be, of course, equal to 0. And we already know the probabilities are between 0 and 1, so that's not going to be a very useful statement. So this particular Chebyshev's theorem perspective is only going to be useful when we want to look at the probability that you're within 1 standard deviation of the mean, or 2 standard deviations of the mean, or 2.5 standard deviations of the mean, or something like that. But it works for all random variables: normal, Poisson, binomial, hypergeometric, log normal, and so on. So it's very general, but it gives you bounds, not direct approximations, right? Pros and cons. So let's just look at a particular problem that we can solve directly from this. So let's assume that we want to know what is the probability that we're. I'm not going to draw a normal distribution. I don't want to have a misleading picture here, right? So some weird distribution. So what's the probability that you're within, say, 3 standard deviations of the mean, right? So we have some area, right? Let's call this area A. So do we have some bounds or approximations on this? And the answer is, of course, yes, right? So k here is going to be equal to 3, right? K is equal to 3. So within 3 standard deviations of the mean. So the probability that you're within 3 standard deviations of the mean, according to Chebyshev's theorem, is going to be greater than or equal to 1 minus 1 over 3 squared, right? So what is 1 over 3 squared? So that's going to be 1 minus 1 over 9, which is going to be 8 over 9. That means the probability that you're within 3 standard deviations of the mean is always going to be approximately equal to 88.89%, right? That's going to be for all random variables, right? So keep in mind, for example, the normal distribution, it's always 99.7%, which definitely satisfies that. But regardless of the distribution, you're always going to have about 89% of the data or more between 3 standard deviations of the mean. So that's pretty interesting. Now, what if we want the complement of this, right? So one can also phrase Chebyshev's theorem from that perspective. So what's the probability that you're more than k standard deviations from the mean? So one can easily show that's just going to be 1 over k squared, right? So keep in mind, this is only useful for k is bigger than 1. Same exact assumption, because if k is equal to 1, we know that that's going to be equal to 1. So that means this is going to give us an upper bound for the probability, right? So the probability that you're within or more than 5 standard deviations of the mean is going to be at most something, right? And we always have a lower bound for that because we're always greater than or equal to 0, right? So let's look at a particular distribution that we may occur, right? So let's assume this is our distribution. Very strange looking, but who cares? And let's assume we want to be within 4 standard deviations of the mean, but not within 4, actually beyond 4 standard deviations of the mean. So we're scared of the mean, so we want to be somewhere over here. So, right? So what's the probability or a bound on that probability? Right? So this is our area hanging out there, and our k value here is going to be 4. Keep in mind, Chebyshev's theorem, at least this form of it, only works on symmetric distances from the mean, not asymmetric. There are generalizations for that, but of course the probability becomes, the statement becomes a little bit more complex. So according to this area is going to be less than or equal to 1 over 4 squared, which is 1 over 16, which we know is going to be 0.0625. So regardless of the shape of this distribution, the probability that we're more than 4 standard deviations of the mean is going to be at most 6.25%. right? So that is what Chebyshev's theorem does. It gives you approximation bounds on symmetric distances from or within the mean and also beyond the mean, because they're of course complements of each other, right? So of course these bounds are not that precise, right? So it's not that precise. Although, 6.25 doesn't really seem that much, but this is of course a subjective statement. But it holds for all random variables, regardless of distribution, regardless of mean, regardless of standard deviation, regardless of discrete or continuous. This is always going to hold. So of course, pro and con, you give something, you take something back. The bounds are not that precise, but it holds for all random variables. That's the Chebyshev's theorem. But do keep in mind there are formulas that give you bounds. For example, the probability that you're between two arbitrary values, for example, a less than x less than equal to b, that of course is a more ideal statement that we will be happy with, right? Because then I can ask, well, what's the probability that you're between 30 and 42 for any random variable? That's going to be a very difficult question to answer, generally speaking, but there are some approximations under some assumptions that you can investigate, but I'm not going to go into that here. So now let us look at a couple other problems that we can use approximations for that are often seen in the real world. So the next discussion that we're actually going to look into is guided by the premise that some distributions approximate others. If you remember from our discrete discussions with like binomial, hypergeometric, Poisson, and so on, a lot of these variables are similar to one another in their approximations and the problem they solve, but they only vary by a slight assumption or a slight variation of the assumptions, right? So let's actually go back in the day and recall one derivation that we actually went through. So recall that if x is a binomial random variable, then its distribution is always going to be represented by Cnx times 1 minus the probability of success times m minus x to the power, to the power m minus x, and then p to the power of x, where n is the number of independent Bernoulli trials that you execute, and p is the probability of success, and x is the number of successes you want in that particular sample. So where did Poisson come from? So what we began by doing was defining p to be equal to lambda over n, or equivalently lambda is equal to n times p. So n times p was the expected value of a binomial distribution, lambda the expected value of a Poisson distribution, so having these two equate to each other is a nice way to derive the Poisson distribution. So from this definition, we see that as n tends to infinity, the probability of success is going to be close to 0. So once we actually send n to infinity, this distribution actually becomes the Poisson distribution, right? So pxx, where x is Poisson, and technically you can call it py, so you don't have different x's floating around. And actually, let's just go ahead and do that. Let's just call it py, so you don't confuse x and y here. So that's going to be equal to e to the, so that means, I guess we could say that px is converging to py. And that's going to be equal to e to the minus lambda times lambda to the x all over x factorial, and that gave birth to the Poisson distribution. So now, what if n is not exactly equal to infinity, or something very large, and p is not exactly 0, but something really close to it? That creates an approximation, right? And that approximation is actually called the law of rare events. And some people will also call it the Poisson limit theorem. So let's just formally state what this law of rare events or the Poisson limit theorem actually says. So if n is a large subjective term and the probability of success is small, again subjective, then the probability that capital X is equal to X, where X is a binomial distribution, can be approximated by a Poisson distribution, right? That means n choose x times 1 minus p to the n minus x times p to the power of x is going to be approximately equal to e to the minus lambda times lambda to the x over x factorial, where lambda is equal to np. Okay, so let's just look at an example and how we might be able to execute this in a real life problem. Keep in mind this is an approximation, not exact. But the closer or the larger n is and the smaller p is, the better this approximation will be. Okay, so let's just look at an example. So let us suppose 1.2% of a population enjoys watching a certain movie. And you gather a simple random sample of, let's assume, 1,520 people. So the first thing that we need to at least decide in our minds is this a small probability of success, and is this a large sample size n? If you can justify yourself that these two are indeed true, then you can use a Poisson distribution to approximate this binomial type of problem. But keep in mind, this is not technically infinity, right? It's only 1500. That's not 15 million. That's not 15 trillion. It's just 1500, right? And 1.2% is not 0.1% or 0.0005%. So this approximation may be very greedy or may be very off, right? And you can look at the differences between the two, and you can sort of compare the answers that you would get and notice that as p gets really small and n gets really large, then these values actually do get closer together, which is actually pretty interesting, I think. So let's just assume that in our minds that this is indeed small and this is indeed large or small enough so that our approximation isn't far off from what we care about, right? So what is the probability, or what is an approximation to the probability that exactly 15 people in our simple random sample like this movie? Okay, so what do we have here? So the probability of success is going to be equal to 0.012, and the sample size is going to be equal to 1,520. Again, technically, assuming that the likings of this movie for each of these people in our sample is independent, then we should be using a binomial distribution. But what if you think that the binomial distribution formula is complicated, or maybe these factorials grow super large and your calculator can't handle it? Then you would have to have an alternative, right? So if you can justify to yourself again that this is small and this is large, then what we can do is we can approximate n times p, right? So the expected value of x is going to be n times p, which is going to be approximately equal to 18.24. This is what we're going to be defining to be equal to our lambda for the Poisson distribution. So that means the probability that we have exactly 15 successes is going to be approximately equal to e to the minus lambda times lambda to the power of 15 all over 15 factorial, which is going to come out to 0.0754. Now, is that the exact answer? The answer is, of course, no. The probability that x is equal to 15 should be equal to 15, 20 choose 15 times 1 minus 0.012 to the power of 15, 20 minus 15 times 0.012 to the power of 15. I invite you to see what this actual answer comes out to, and then compare the differences between the two. But you should see that these two are relatively close. They're not super far away. It's not like 7% versus 82%. It's not going to be that far off. But you can decide for yourself whether this is a good approximation or not. So let's look at another distribution approximation that is actually very commonly used in practice. In our exploration of probability theory, we have actually discussed two main types of random variables, in particular discrete and continuous numerical random variables, right? And the solution strategies for doing probabilities on each of these problems are completely different, right? One uses calculus and the other does not. So is it possible to approximate one with the other? For example, can we use discrete to approximate a continuous distribution because maybe we don't know how to use calculus? Or maybe if we're solving problems like, what's the probability that x is bigger than or equal to 52? For example, Poisson, we have to do this in the complement, but the complement is 51 down to 0, which is still big. Is it still possible that we can approximate this with a continuous variable with like an integral from 52 to infinity? And the answer is indeed yes. Now, the stories associated to, what are the pros and cons and is there bounds on the estimates between these conversions really depend on the distribution, and we're not going to get into it here, but we're going to give one example that is commonly used, at least in basic statistics, that you might want to take advantage of in a couple occasions. So the theorem that we're actually going to be looking at is going to be referred to or is known as the de Moivre-Laplace theorem. So the de Moivre-Laplace theorem. De Moivre-Laplace. So what does the de Moivre-Laplace theorem say? So it says this: if n is large, again that's a subjective term just like we had for the Poisson limit theorem, then the probability that x is equal to x, where x is a binomial random variable. So notice that we're approximating the binomial distribution again, but we're not assuming anything about the probability of success. This can actually be approximated by the probability that y is equal to x, where y is a normal random variable, where the mean of this distribution, mu y, is going to be equal to n times p, and the variance of this random variable y is going to be equal to np times 1 minus p. Now, where are these coming from? That's the expected value of x, and that's the variance of x, right? So those are good choices for the variance of y and the mean of y, right? And that's pretty much the story of that. Now, we're approximating a discrete random variable with a continuous one, so there's of course going to be some error there, in addition to the error of approximating these values, right? Because in the continuous world, we're going to be including all of the non-integer values as well, right? So the probability that we're between 5 and 6 is going to include 5.1, 5.2, 5.3, right? So as long as the distribution is practically small and close to the horizontal axis, they should not be accumulating too much area. All right, so let's look and see how we can actually use the normal distribution to approximate a binomial random variable. So let us suppose that 76% of a population, right, so that's clearly going to be our probability of success P, and we're not going to have any bounds on that, so that can be as large or as small as we want, which is actually pretty great. And let's assume that this subset of the population enjoys exercise. If you attain a simple random sample of 7,650 people, so again, we're going to have to ask ourselves, is this large, right? Because that's the assumption of the de Moivre-Laplace theorem. What is the probability, or what is an approximation to the probability that between 5,700 and 5,800 people in our sample likes exercise? Okay, so how are we going to go about this? So what is the mean of our normal random variable y going to be equal to? So that's going to be equal to n times p, assuming that we have decided that this is large enough, or the error in these approximations is not going to be significant to us. So that's going to be approximately equal to 7650 times 0.76, whatever that is equal to. And then the variance of our y is going to be equal to np times 1 minus p. So that's actually not an approximation, that's exactly equal to each other. And this is going to be 7650 times 0.76 times 0.24, right? And you can figure out what those are going to be equal to. So what are we going to be substituting these into? So these are going to be substituted into our normal random variable distribution, right? So 1 over the sigma square root of 2 pi times e to the minus 1/2 x minus mu over sigma the quantity squared. Now, sometimes software does not do integrals on distributions like this very well, especially if these parameters are really large or really small, right? So sometimes it's beneficial to be converting into the standard normal world for all of your conditions. And if you're doing probabilities via z-tables or so on, you have to convert to z-scores in the standard normal anyway, right? So let's just go ahead and go through that process just to make sure we know how to do that. So remember that the z-score for a particular value is going to be equal to x minus the mean all over the sigma of the normal distribution. So that's going to be mu, and the square root of the variance is going to be our sigma. So once we have that, then the area that we want, so the probability that x is in between 5,700 and 5,800 is going to be equal to exactly the probability that the z-score for 5,700 is less than or equal to the z-score for x is less than or equal to the z-score for 5,800, right? So whatever those numbers are, we find them. And then how are we going to find this? So remember, the distribution for a z-score distribution is going to be equal to 1 over the square root of 2 pi e to the minus 1/2 x squared, right? So if we're in the calculus world, then we're just going to be integrating from the z-score of 5,700 to the z-score of 5,800 of the standard normal distribution. And you're going to come out to approximately 0.3528, right? Or you can find the cumulative density function evaluated at 5,800, find the cumulative density function evaluated at z-score of 5,700, right? So that's going to be f of z of 5,800 minus f of z of 5,700. You're going to get the same exact answer as we already know, but this would be your z-table approach in order to obtain that answer. So those are just some of the approximation procedures and strategies that you may have involving Poisson, binomial, normal random variables, and also a couple bounds and approximations for normal random variables, and technically any random variable, discrete or continuous, that you may be interested in modeling. Anyway, I hope you enjoyed this video, and I'll see you next time. Take care.